Howdy, everyone. How is everyone today? Good to hear. That is good. Alrighty, let's jump right into it. So I will be holding office hours for the first time today after class, like directly after class. So I'll end this meeting and then I'll jump over to the office hour Zoom meeting, which you can find along with all the other lecture Zoom meetings. And I'll be doing office hours directly after class on Thursdays and Mondays. And I realize that doesn't work for everyone, but if you want to meet and those times don't work for you, then email me through Canvas and usually we can find some time to meet. But yeah. Okie doke, let's get started. All right, so let's finish up talking about dot product. So we're going to talk about how we use the dot product to do orthogonal projections of one vector onto another. So suppose we have the following situation. So for simplicity, I'm going to draw one of the vectors as horizontal, but it does not have to be horizontal, obviously. But I'll call this guy V. And then suppose we have another vector which starts in the same place, or we will start it at the same place, rather. Call that guy U. So consider the line containing V. Let me just draw that in black also. So consider V to be sort of parallel to the ground. I drew it kind of horizontal here, but V could be whatever. But suppose the line containing V is, think of that as like the ground, right? We have some other vector U. We're going to start these guys at the same place. So basically what we want to do is we want to think of like light shining directly down onto the ground. Think of like the sun shining down onto the line containing V, which we consider to be the ground. Here's our sun. That's actually not very good. Our sun shining sort of straight down orthogonally onto the ground. So look at the shadow that is going to be cast by you onto the ground, right? The line containing V. So here's the tip. And then if we look at the vector which starts, good Lord, it's bad today. It starts where U and V start and ends at the tip of that shadow here. This guy here. So that shadow right there is going to be the projection of U onto V. So we write it like that. So think of the line containing V. If you look at the shadow of U onto V, if you have a light source kind of shining orthogonally down, oh my God, why is it doing that constantly? Orthogonally down onto V, just at a right angle. If you look at the shadow, the vector which starts where the two start and end where the tip of the shadow ends, that's the projection of U onto V. That vector is the projection of U onto V. And we write it like this right here. So it's like the vector U and then the two parallel lines. So that means parallels, we'll see in a second, and then sub V. So projecting onto V. Not quite. For two reasons. So it's the thing itself is a vector and not just a component, which is, so a component of a vector is just a scalar. So this vector projection is actually, we'll talk about component, but this vector projection is, here is a vector itself and not just a component of a vector. Number two, I drew V horizontally. So in this case, it would kind of be like the I component of U related to that, but I can draw V however I want, right? I could draw V like this and say this is my U. And then if I look at the line containing V, consider that to be my ground, and look at the orthogonal projection down onto there. So here's the shadow of U onto V. Then that projection, oh my goodness, why does it do that? Then the projection of U onto V is no longer going to be pointing in the I direction. So you're always going to get a vector parallel to V, right? Because it points either in the same direction as V, as this one does here, or points in the opposite direction of V. But it's always going to be parallel to V. So we think of the projection of U onto V as not the component. Now think of it as like the part. Sorry, it is particularly bad today. I will try to remember over the weekend to look at something else to write on because this is obnoxious. So the part of U, which is parallel to V. That's how we think of the projection of U onto V. Sorry, is this making sense so far, what the projection is? Does everyone understand how that works? It's just like the shadow of U on the ground containing V. And you're always going to get something parallel to V. Okay. So let me draw that again, and then I will just write down the formula, and then I'll explain sort of kind of where it comes from, but I don't want to dwell on that for too long. No, so this, the part that makes a right angle with the ground is this piece right here, right? So you can think, well, we'll talk about this in a sec. You can break U into like the parallel part, the part which is parallel to V, and the part which is orthogonal to V. So the part which makes a right angle with the ground, sort of this guy here, is not what we're looking at. We're looking at the red piece, the piece which is actually parallel to the ground, where the ground is what contains the line containing V. Okay, so let me draw a picture again. So here's our V, here's our U. If we sort of project orthogonally down on V, that's projection of U onto V. Okay, so how do we get this? Here's the formula that we use. Also be careful. So make sure you don't mix up U and V in this case. The way we'll remember this in relation to the formula also is note that V is on the bottom in this subscript, all right? So V is on the bottom. V is the guy being projected onto, right? V is the ground. So remember that. Okay. So the formula for the projection of U onto V is, so U dot V over V dot V. So that's a scalar, right? U dot V is a scalar, V dot V is a scalar, times the vector V. And so another way to think of this is U dot V over magnitude V. So remember, V dot V is magnitude of V squared. So we're going to think of that as magnitude V times magnitude V. So it's that. Why? Really? Times V over magnitude V. So that V dot V just became magnitude V times magnitude V, and we just kind of pulled that 1 over magnitude V out. And so this guy so we got our U dot V over magnitude V still. And this V over magnitude V is the unit vector pointing in the direction of V, right? Remember the way you take a non-zero vector and you turn it into a unit vector pointing in the same direction is you divide by its magnitude. So remember we write that as E sub V. Kind of use E for unit vector. So that's a unit vector pointing in the direction of V. So you can remember this formula if you like, but this is the way you kind of want to think of it. I find this the easiest way to remember it. So this guy here, this U dot V over magnitude V, that's the component of U on V. Make sure that's obvious that is a V there and not another U. Right, remember we talked about components of a vector? So we can think of a vector. I'll do it in R2 here real quick. So in R2, if we have a vector, so if it goes A along the x-axis and B along the y-axis, we think of this vector as AB, right? In fact, what A and B are the projection of v onto the x-axis, or if you think of it, the vector I pointing in the positive direction of the x-axis, A is the projection of v onto I in the same way, right? If you do the shadow, you're going to get a vector of length, magnitude, or square root, or absolute value of A pointing in the direction of I, or in the opposite direction if it points in the opposite direction. But A is the component of V onto I, and B is a component of V onto J. So it's the same sort of thing here, except now we're not projecting our vector onto I, we're projecting it onto just some other vector V, right? So it's the piece which is parallel to the vector V. So remember we said a vector V, or let me do U in this case. So you can think of a vector U as let me write it like this, as a magnitude of that vector times a unit vector pointing in the direction of U, right? So the projection of U onto V is sort of similar. It's the unit vector pointing in the direction. So either it points in the direction of V or in the opposite direction of V. And it's the magnitude of that times that. But that's basically what the component does. It's sort of like this, like the magnitude, except it could point in the opposite direction. But the dot product takes care of that, right? Remember, if the angle's obtuse, the dot product's negative, so you're going to get something pointing in the opposite direction. And if the angle theta between U and B is acute, they're kind of pointing in the same direction, you get something positive, and you get a vector pointing in the same direction as U. Sorry, a lot of that was kind of extraneous, but this is what you need to remember. So either just remember this formula here, or remember this here. And you do need to know what the component of U on V is.
How did you get the vector V over the magnitude of vector V, like in the second equivalence?
So and down here we had V dot V. And remember, if you take the dot product of a vector with itself, you get the magnitude of V squared, right? So I just thought of that as magnitude of V times magnitude of V. Well, here's magnitude of V here, here's magnitude of V here. I just sort of split them up in a way that's convenient to think about it.
Okay, that makes sense.
Okay, I could probably say some more about that, but I need to move along here. What does the E represent? Yeah. So E, it's just sort of kind of a universal thing for unit vector. So it's just denoting it's a unit vector, and the sub V means it's a unit vector pointing in the direction of V. Okay, any other questions before I do a quick example? Okay. All right, so let's find the projection of U onto V. Where U is going to be the vector 5, 1, -3. And V is going to be the vector 4, 4, 2. And let's just also find the component of u on v, just to remind ourselves what that is. Okay. So remember, u, the projection of u onto v is u dot v over v dot v, so that's a scalar, times a vector v. So u dot v, so we take the dot product, we multiply the corresponding components together and add a bump. So we get 5 times 4, which is 20, 1 times 4, which is 4, and 3 times -2, which is -6. V dot v, multiply the components together, add them up. So we get 4 times 4, which is 16, 4 times 4, which is 16, and then 2 times 2, which is 4. And then that's times the vector 4, 4, 2. So 20 plus 4 minus 6 is 18. 16 plus 16 plus 4 is 36. So on an exam, that's a perfectly fine answer. Could be simplified, of course, but that's the correct number. That's fine. But we can simplify it. 18 over 36 is 1/2. You multiply a vector by a scalar, you just bring the scalar inside and multiply each component. So 1/2 times 4 is 2. 1/2 times 4 is 2. 1/2 times 2 is 1. And that's a projection of u on v. So the component of u on v, remember, is just u dot v over magnitude v. Useful to remember, but not as important. Add what two components? Add those components together at the end, which the 2 to 1, because the formula, remember the thing we're getting is a vector, right? When you project a vector onto another, you get a vector, which is parallel to the guy you're projecting onto, right? So the formula is, so you get a dot product divided by a dot product, that's a number, and then you multiply that by a vector. So it's a scalar times a vector, which is a vector. So a projection is a vector. The component piece is a scalar itself, but the projection is a vector. So u dot v over magnitude v. So we already said u dot v was 18. Magnitude of v, remember, is v dot v is magnitude v squared, which we already calculated. And we saw that the magnitude of v squared, thus, is 36. So the magnitude is going to be square root of that, which is 6. So we get the component of u on v is 3. Any questions about that? Oh. Sorry, I feel like I'm moving quickly, but also spending more time on this than I wanted to. So it's a lovely combination. Okay, so that's it for the dot product. Now we're going to look at the next chapter, where we talk about the cross product of two vectors. Right. So we said there are kind of two different ways to multiply vectors together, although we don't usually think of it like that way. But we saw one of them, the dot product. You take two vectors, you take the dot product, you multiply them together, and you get a scalar. So the dot product, you multiply two vectors together to get a scalar. The cross product is the other way. We can multiply two vectors together, and that's going to give you another vector. So before I define the cross product, we kind of have to talk about a few things, but suppose this is our vector. No, I want that to be v actually. V, and that's our vector u. So cross product is only, I want to emphasize this, only defined for vectors in R3. So the dot product, you can take the dot product of vectors in R2, right? You just multiply the components together, add them up. That's perfectly well defined. Cross product is only defined for vectors in R3, right? Not for vectors in R2, not for vectors in R4 or anything above, only for vectors in R3. And here's the reason why. Here's what the cross product is. Suppose you have two vectors u and v, and you want to find a third vector, which is orthogonal to both of these guys. This will be useful in a moment when we, next chapter, when we start talking about planes. This sort of thing will be very useful. But suppose we have two vectors in R3, right? So think of those two vectors as lying like parallel to a desk, right? And you want to find a third vector which is orthogonal to both. So we're going to call that guy u cross v, the cross product of u and v. This vector is going to be orthogonal to u, and it's also going to be orthogonal to v. So this is a reasonable thing to do in 3 dimensions, right? If you have two vectors parallel to your desk, right? Vectors which are orthogonal, perpendicular to both, would be pointing straight up or straight down, right? Those are basically your options, but there's always a vector perpendicular to both as long as u and v are not both. Well, that's fine. But if we're in R2, right, suppose I have two vectors u and v. So all the vectors which are orthogonal to u lie either in this direction or in this direction, right? They point in one of those two directions, that way or negative in that way. And all the directions, all the vectors which are orthogonal to v are either pointing in that direction or that direction. Notice there are no vectors in this case which are orthogonal to both u and v. And that's usually going to be the case in R2. So this is sort of where the cross product comes from, but it only is defined for vectors in R3. Okay, so before we define the cross product, in fact, let me just define the cross product, and then we'll look at an easy way to remember. This is how you're actually going to remember it and how you're going to compute it, but I'll just write down what the cross product is. So let me do v and w actually. Suppose v is a vector v1, v2, v3, and w is a vector w1, w2, w3. then the cross product of the two, V cross W, is going to be kind of a mouthful, V1W3 minus V3W1. V3, nope, I already screwed it up. Sorry, that should be twos, not ones. So V2W3 minus V3W2, don't worry, you're not going to memorize it like this. V3W1 minus V1W3, and then V1W2 minus V2W1. So those are the three components. There's kind of a lot in there. And if you stare at it and squint your eyes, you can see some patterns in there and maybe think of a way to remember that. But we'll have a better way to actually remember how to calculate this. But that is the definition of the cross product for now. But let's look at an easier way to remember that. We're going to use determinants of matrices. So if you've taken 220, you can probably zone out for a few minutes because you've done this to death. But we're going to use determinants to remember the formula for this in a much more compact and easy way. So we calculate determinants of square matrices, right? So a matrix is an array of numbers, a rectangular array of numbers. So if we have as many rows as we have columns, you're a square matrix. So if you have 2 rows and 2 columns, so suppose we have the matrix A, B, C, D. I'm not going to talk about what this means. We're just going to define the determinant of this matrix. So the way we write the determinant of a matrix is you put in the entries and then you do sort of square brackets around it, straight lines. So for a 2 by 2 matrix, what you do is you multiply the diagonals together. So A times D, B times C, and then you subtract them. So the main diagonal, the one starting with the very first entry, is the positive guy, so AD minus BC. Right, so you multiply the diagonals. The main diagonal is positive, and then you subtract the off diagonal. Pretty simple. Not going to explain where that comes from. All you need to do is remember how to calculate it. So for example, what's the determinant of 3, negative 2, 2, 1? What do we get? Right, we get 3 times 1, which is 3, minus negative 2 times 2, which is negative 4. So 3 minus negative 4, 3 plus 4 is 7. Easy peasy. Okay. So if you've taken 220, you probably remember determinants. When you start adding, every time you add a new dimension to your square matrix, calculating the determinant becomes like exponentially more of a pain in the ass. But the way you can do it is, so for 3 by 3 determinants, which is the biggest we're going to need, but you're going to turn it into 3 2 by 2 determinants. So here's how we calculate 3 by 3 determinants. So suppose we have a 3 by 3 matrix, A1, B1, C1, A2, B2, C2, A3, B3, C3. We take the determinant. Here's how we're going to do that. Here's the process, right? So when you're starting out, it's easy to forget the minus sign here. So what we're going to do is we're going to go along the top row. So A1, B1, C1, right? So just go do plus minus plus along the top, just to remind yourself. So we're going to do this in 3 pieces. So you're going to go along the top row, A1, B1, C1. You're going to start with the first entry, A1. Why does it do this, man? Okay, A1. And you're going to write that down. Then you're going to cross out the row and column containing A1. Let's just put the plus here, which lies above it. Oops, no, that's right. So the row, cross out the row and column containing A1. Why do you do this to me? There we go. When you do that, you're left with a 2 by 2 array of numbers, right? The B2, C2, B3, C3. We're going to take the determinant of that and multiply it by the A1. B2, C3, oops, nope. Sorry, my goodness. B2, C2, right? B3, C3. So we have positive plus A1, the first entry, cross out the row and column, multiply by the determinant of the remaining guy. So then we do that for the second entry, B1, and then for the third entry, C1. So when we do that, do the same process. So go to the second entry, B1. It's negative, which is why we put the negative above it. You can't forget that or else you're going to get the wrong thing. So minus B1, and then cross out the row and column containing B1. You're left with a 2 by 2 array of numbers. Multiply by the determinant of that. So times the determinant A2, C2, A3, C3. And then do the same for the third entry. So plus, sorry, I didn't have enough room on the right, but this is just, these are all numbers we're adding up here. So plus because we wrote the plus above C3. Sorry, C1 rather. So plus C1. And then cross out the row and column containing C1. And multiply by the determinant of the remaining guy. A2, B2, A3, C3. Wait, which should what? Yes, you're correct. Yes, you're correct. Sorry. Sorry. Don't need to make this more confusing. Yes, you're correct. Yeah. Good eye. It's testing you. Good job. Okay. So it's just that process. Remember the plus minus plus, and then go along the top row. Take your entry, cross out the row and column, multiply by the determinant, move along to the second and then the third. You'll do this a bunch, so you'll get the hang of it. But as a quick example, let's take the determinant of this guy. I'm going to move really quickly, but just do your plus minus plus, Takes like 2 seconds, and it makes sure that you don't forget the negative sign on the second one, because that's going to throw you if you don't do it. Okay, so we start with the first entry. Cross out the row and column containing that. So positive 1 times the determinant of 1, 1, 3, 2. We'll calculate that in a sec. Then move on to the second entry. It's a minus. So minus negative 2. Can't forget that minus. Cross out the row and column. Multiply by the determinant of the remaining entries. 3, 1, negative 2, 2. And then do the same for the third. So plus, 0. Cross out the row and column containing. Take the determinant. Doesn't really matter because we're multiplying by 0, but I'll write it down. 3, 1, negative 2, 3. Okay. So determinant of 1, 1, 3, 2. It's going to be 1 times 2 minus 1 times 3, which is negative 1. Determinant of 3, 1, negative 2, 2 is 3 times 2, which is 6, minus 1 times negative 2. So 6 minus negative 2 is 8. And then this determinant is going to be 11, but we're multiplying by 0, so it doesn't matter. So 1 times negative 1 is negative 1. Minus negative 2, so plus 2 times 8 is plus 16. And then plus 0 times 11. So we get 15 for our determinant. Okay. So here's how we're going to use 3 by 3 determinants to define the cross product. Nope, let me do V and W. So a V is a vector V1, V2, V3. W is a vector W1, W2, W3. We're going to define V cross W as a 3 by 3 determinant. And this is going to be way less to remember than that original definition. It's equivalent, but you can remember it as just one nice, easy thing. So it's going to be the determinant of the following. So the determinant of the 3 by 3 matrix, where the top row is I, J, K, the vectors I, J, and K. So this might look kind of weird because we're putting vectors as entries in our matrix instead of numbers, but don't think about it too hard. Just do the process and you'll get the right answer. So the top row is I, J, K. The second row is V1, V2, V3. The vectors in your first vector in order matters. So this has to be the components of the first vector in the cross product. And the third row are the components of the second vector, W1, W2, W3. So when we do this, this is how you're going to remember it. But if you write it out, you get I times determinant V1, V2, new, V2, V3, W2, W3, Y. I, J, and K, so you have to know this, right? I is 1, 0, 0, the unit vector with 1 in the first component, 0 everywhere else. J is 0, 1, 0. and then k is 0, 0, 1. Those are three very important vectors, which is why we give them their own name. So then minus j, cross out the row and column, determinant v1, v3, w1, w3, and then plus k times the determinant, cross out the row and column, v1, v2, w1, w2. That's a cross product. You don't need to remember the stuff on the right-hand side. You need to remember just this determinant guy, and then know how to calculate determinants, and you'll be fine. But note, let me mention one thing. So remember, when you have there are like two different ways we can write a vector algebraically. Right? We can write it as the vector ABC and components like this, or we can write it as A times I plus B times J plus C times K. Right. Whatever you multiply by I is going to be the first component of your vector. Whatever you multiply by J is going to be the second. Whatever you multiply by K is going to be the third component of your vector. So here, this is the first component of our vector. This is the second. This is the third. But don't forget the minus sign here. So you'll have to flip whatever's in there. Okay. Any questions about that formula? I guess we'll do an example, and then we'll leave it there and then pick it back up tomorrow. So let's calculate the cross product of -214 and 325. Okay, so we do our determinants. So ijk is the top row. Second row is the entries of the first vector, which is -2, 1, 4. Last row is the entries of the second vector, 3, 2, 5. And just to remind ourselves, let's do our plus minus plus. So we have I times, cross out the row and column, determinant of 1, 4, 2, 5. And then we have minus j, cross out the row and column, determinant of -2, 4, 3, 5. And then plus k, cross out the row and column, times the determinant of -2, 1, 3, 2. Okay, so really quickly, the determinant of 1, 4, 2, 5, this first guy, so it's 1 times 5 is 5, minus 4 times 2 is 8, 5 minus 8 is -3. So the second determinant of -2, 4, 3, 5, is -2 times 5, which is -10, minus 4 times 3, minus 12, -10 minus 12 is -22. And then determinant of negative 2, 1, 3, 2 is going to be negative 4 minus 3, which is negative 7. So we get negative 3 times I. So that means the first component is negative 3. And then minus j times negative 22. So that's minus, oh, come on, man, negative 22, which is positive 22. And then plus k times negative 7. So the third component is negative 7. So yeah, negative 3, 22, negative 7. You can write it like that, or you could leave it as the negative 3 I plus 22j. So remember, don't forget the minus. So minus negative 22 is 22, and then minus 7k. It's mean the same thing. Okay. So if you don't have any questions, I'll be moving over to the office hours meeting. So you can come there if you have any questions about anything in class or anything else or homework, etc. But yeah, if you have any questions, please show up. That's what the office hours are for. And if not, then I'll see you guys tomorrow, and we'll finish up talking about this chapter and then start talking about planes. And yeah, have a good one.
Thank you.
Thank you.